Geotrig, lesson 5, day 3. We're going to continue working with square roots of negative numbers, which therefore leads you to poke an eye out, sometimes literally, sometimes figuratively. Mr. Havacek definitely uses that phrase, and I've picked it up from students of his. So let's actually start this problem. I'm going to fix it. There, made it a little bit larger so that we can work with it, be a little easier. Now, this is my process for fixing or simplifying addition of multiple square root stuff. I'm going to make several passes through this problem, and each time I make a pass, I am going to fix certain parts. So the first thing I'm going to do is make a pass through, and I am going to try to simplify square roots that I know are perfect squares, and I want to poke any eyes out where I'm taking a square root of a negative number. So the first one I encounter is square root of negative 3. I don't like square root of negative 3, so I'm going to take the I out, or the negative off, and put it at the end and make it an I. Can I do anything with square root of 3 though? So square root of 3, maybe I'll even just put it right behind the square root that I'm dealing with. And square root of 4, though, is 2. So know that there is a multiplication between all of those. Plus, there's a 3. I'm going to leave it. The square root of negative 2 becomes square root of 2i. The square root of negative 9 becomes the square root of 9i. But the square root of 9 is, so it becomes 3i. Notice, though, that all of these pieces, the 3, the square root of 2, the I, the 3, and the I, are all multiplied. It's very important. Don't add signs into it. Don't take signs away. Plus, what? 4i plus 4. And now, all we have to do is see if I can simplify anything else. Put things in order. I like to put i's at the end. I think the book sometimes put i's before the square root because, and don't write this down, is because there's a big difference between this and this. The square root of 3i it doesn't work that way. You don't put an I inside the square root. So this one is not a good option. This is what you would write it as. So be careful on how you write things. But okay, I'm going to just kind of put things in order. I have a square root times I times 2. If I put that in simplified form nicely with our coefficients first, hopefully everybody recognized that that would be what? 2 square root of 3i. Nothing groundbreaking there, right? I didn't change anything. I just reordered to make it a lot easier. Now, I could reorder this one. Maybe we should just reorder first. So that would be plus 3 times square root of 2i, correct? And the next one is plus 4i. Nothing changes, plus 4. And now my next step is I can obviously clean this one up here because I times I is negative 1. 3 times 3 is, so this is not a positive 9, it becomes a, so 2 square root of 3i minus 9 square root 2 plus 4i plus 4. Is everybody okay with that? You guys got one more minute yet. So, we are not done with this problem. This problem, guys, needs to be written in complex standard form. Complex standard form is what again?
Oh, you have to put the i's, or say plus pi.
a plus bi, so I'm going to write that off to the side here. I'll change the colors for you. It's a plus bi. Now, to get it into the form of a plus bi, I need to put the real stuff first and put the imaginary stuff second. So of our numbers, what's real? Is this real?
No, because that's 9.
This?
Yes.
This?
No, in the 4.
And the 4. So I need to put this, the negative 9 square root of 2 first with the 4. So negative 9 square root of 2 plus 4, right? And then I'm going to go back and place plus 2 square root 3i plus 4i. Well, all you did, Mr. Konchak, was just move stuff around. That's right. But here's the thing. I can group all of this, and what letter would that be? What letter would this be? A.
Oh, A.
And the only thing is if I go up to here and say I want to create this all to be B, that can't be. That cannot be B. Why? Where? No, not because it has a square root. There's more than one I. I should be at the end of B. I needs to be here with B in front. So that means, wait a minute, this has an I, that has an I. What can I do with the I? No, not necessarily. Because, think it, this is a square root of 3. There's no square root of 3's over here. They're not like terms directly. What can I do with the i's, though? Take it out. It's Fall Fest coming up, so take it out. Yes. And if I take I out, I'm going to put it at the end because that's where it belongs. And what's left is 2 square root of 3 plus 4. Now you have A, you have B. You have your real and you have your imaginary component. Done. That's what your book is going to expect you to have. So the ratio of two areas of similar geometric figures equals the square of their scale factors between them. So we have a scale factor of 4 between these two rectangles. That means if this is W, then what's this?
W.
It's 4W. If this is L, then this has to be because of the scale factor, right? It's 4 times the size. Now, happens to be, how do you find area? Length times width. So, would you guys agree that area would be length times width for the small triangle? Or rectangle, sorry. Yes? What's the area of the larger rectangle? 4W times 4L. Yes? And 4 times 4 is? 16. I'm going to change the order to say LW because we have LW on the left over there. But it's the same thing, right? Now, we said that there's a scale factor of, from the big one to the little one, would be 4 to 1. That's the scale factor. That's what it means. That the size of the larger one is a 4. That means the size of the side of the smaller one is a 1. 4 to 1, 1 to 4. Matters which way you're looking from. Yes?
Yes.
Now, according to the statement above, is that that ratio of areas would just be the square of that. So you take the scale factor between two similar figures, and you would exactly know the area ratio as well. So this works for the scale factor. What happens to the area ratio of big to small? Actually, I should be small in there. How did I get an L? Nobody caught it. big to small. If I do just the areas, what's the area of the big one again? 16 LW. What's the area of the small one?
4 LW.
Just LW. What happens to the LWs? It'd be 16 to 1, yes? What's the connection between 16 and 1 and 4 to 1? According to this statement, if I take the scale factor and I square it, I'll end up with the 16 to 1, which is the ratio of the areas. It doesn't matter if we're talking about this nice shape here or some 25-sided similar polygons. If you know the scale factor between them, you know the ratio of the areas. Or if you know the ratio of the areas, you can take that and square root it to find the scale factor. It's awesome. So, use it. Put it to practice here, guys. I will fix that number there. That's 3r over 5. Okay? That number right here. So, the radius of one circle is r. And the radius of a second circle is 3r over 5. What is the ratio of the area of the first one to the second one? Ratio of the areas. I'll give you guys a hint. All circles are similar. They all have the same shape, do they not? Bless you. So, how about I draw this out, guys? What's the first one? That has a radius of r. The second one is the second one is 3r over 5. Is that a bigger circle or a smaller circle? 3/5 of r. Is that bigger or smaller? Smaller, guys. So this would be 3/5 of r. The second one is smaller than the first one. They, though, want to know what's the ratio of the areas. Well, what's the only thing that defines a circle? Well, two things, really. There's a center and its radius. You have something about the radius, or radii? Can we compare them? And if you compare them, that creates a scale factor. And if I know the scale factor, all I have to do is square it. Remember, we have to go from the first one to the second one. So the first one to the second one, what is the factors? R over 3/5 R. What's the scale factor? I purposely wrote it this way because they give it to you, actually, in the problem they actually give it to you just slightly different. Maybe I shouldn't write it that way, but it's okay this way. Yeah, the R's are going to cancel. So you're still left with 1 over 3/5. I don't like to divide by fractions, so I not just move it to the top, but multiply by the reciprocal, so this actually becomes a 5 over. That is your scale factor. I now take this and do what? And so the ratio of areas happens to be 25 to 9. Done. Guys, this one, this problem, guys, can be done very quickly or take a really long time. So we're going to go the really long time right now. But at the end, we will find out that the really quick method is something really close to what you guys know. The whole point of this problem is that you got a box and you want to maybe take a piece of string and connect the opposite corners of the box together. How long of a string do you need? So you want to connect corner B. Corner B is in the front left corner. And you want to connect H, which is way over here at the back top right corner. It's almost the longest distance you could actually cross while still inside the box. Yes? In a straight line. To make this happen, you use the fact that you're dealing with a box, which is all made up of 90 degrees. So, the cool thing about it, I'll use red here, is that I will just traverse the bottom of the box and then take a walk up the box. That forms what kind of triangle? It's a right triangle. So that's kind of interesting. We form a right triangle. And we know right triangle math. What would be the right triangle math that we know? A squared plus B squared equals C squared. So, notice that we are given that the bottom front face is X, the width is Y, and the height happens to be way over here at Z. So, hey, we know Z. Z is the height of our box. I'll put it over there. The question is, what's the distance across the bottom diagonal of my box? Wait a minute, wait. I'm connecting corners B and G. But what's this corner? It doesn't look like it, but what really is it? It's a right triangle. We're just looking at it from a different angle. This is right. So wait a minute. Does that mean that I could find out that distance? Mm-hmm. And it happens to be what? What would that distance be across the bottom of the can? Sorry. I'm going to call it D because it's diagonal. Okay? What would that equal? Maybe I don't want to call it D, but I'll call it D. I wanted to call the other one a D for the diagonal of the box, but this is the bottom. How do I find D? Oh my goodness, guys.
Well, you take X and Y.
Yeah, you know X and Y. So using X and Y, can you solve for D?
Yes.
D squared equals X squared plus Y squared. Wait a minute, I don't want D squared, I want Y. So square root it. So D equals X squared plus Y squared. Is everybody okay with that? This is important because I'm going to change the colors. Is that what happens if I want to find this triangle that I've now outlined in purple? Do we know the bottom base of that triangle? Yeah. It is now square root of X squared plus Y squared. So when I go to fill it in, right, it's the square root of X squared plus Y squared. What's the height? Z. And I'll call this one D2. We'll call the other one D1. I know. Wait, there's another D on there too? Oh, well, they got the D for the point. But isn't this just... We're losing space. I don't have enough here. Isn't that the same thing as saying D2 squared is equal to the quantity X squared plus Y squared with a square root squared? Plus? What's the height? This, guys, this is the base.
There's too many things being squared.
Yes, I know. But look, this is the bottom. The bottom, we said, of this bigger purple triangle is X, the square root of X squared plus Y squared. I have to square that. Then I have to square the height. So the height is squared. But what happens when I square a square root? They cancel each other. And guess what? I'm going to erase the bottom half. So D2, which is our whole entire thing, or actually I'll say it's still squared still. Isn't that just x squared plus y squared plus z squared? And then the final step would be take the, which will equal D2. I basically created the formula, guys. I erased a lot of it, so it's kind of... So using the fact I could take the sides, add them up, or square them, add them, take the square root, please tell me the distance across this box that has the side lengths of m, 2, and 3. The formula says D should equal, we use x squared, so we can use x squared plus y squared plus z squared, which equals the square root of 2 squared plus 3 squared plus m squared. Or wait a minute, what's 2 squared? Really, guys? What? 4 plus 9 plus m squared square root, which equals, sorry, we're squeezing it in here, but it's 13 plus m squared. Done, done, done. Homework is lesson 5, page 47, 6, 7, 19, 21, and 22. Have a great day.